My name's Brock Masowski. I'm the VP of Analytics at Sequant.io, and today I'm going to be talking to you all about net position at risk, a better risk metric for energy retailers. So thanks to everyone for being here and to the conference organizers for this great event. So just a little bit of background for those who may not be familiar with Sequant.io. We are a software as a service cloud-based energy analytics platform. And we work with a variety of stakeholders from retailers to municipal utilities and load serving entities, a variety of different independent power producers. And we provide analytics across the energy spectrum. So everything from market forecasting to asset valuation and really total portfolio analysis. And so one of the things I want to convey in this talk is that it becomes really, really important with today's complexity in the energy markets to capture all the important risk drivers within the portfolio. And that's one of the things that net position at risk does really well. So what drives complexity in modern energy portfolios? One of the things that we're all, I think, very acutely aware of, especially after this last February in Texas, is exposure to hyper-volatile electricity markets, also rapidly changing regulatory requirements, generation technology, and grid dynamics that are evolving at record pace. So the movement within our industry today is faster than it ever has been previously. And so this is something to grapple with. We also have a significant and a growing amount of non-dispatchable intermittent generation. And so we're losing control over when and where that generation is produced. We don't get to determine when the sun shines and when the wind blows. So that is changing the way we have to manage that energy going onto the grid. On the upside, we have access to a broader range of financial products than ever before. Things like exotic derivatives, things like virtual power purchase agreements and proxy generation or revenue swaps, a variety of different contracts that have been developed for the complexity of today's markets. But we have to understand how to use these, and their use really depends on the nature of each individual portfolio. And we also are starting to see customers that demand a lot more than just energy, right? Customers are expecting to receive renewable energy, and they want that to be traceable, and they want to see the trail of where that energy came from and when it was generated. We also have to manage multiple tariff structures to give our customers options, right? And so this trend toward choice is not only at the regional level, but also customer by customer. And finally, management of much more than just energy and cash flows, right? We're looking at things like renewable energy certificates, GHG-free credits, resource adequacy, even carbon is becoming increasingly important. And so we have to be able to manage all these different attributes within the portfolio. So here's an example of a modern energy portfolio, right? It may have supply, it may have demand, it may have exposure to various different risk factors, weather and load and market prices. And so market prices are a risk factor for various different components, things like load, things like market purchases, the value of renewable energy. We also have customer demand that impacts retail revenue, it impacts hedging strategies and market purchases and attribute targets. And then we move on to the hedging strategy for each individual portfolio, and we see how that relates to all these different things. And everything on here affects the company bottom line. So when we start to look at all these interactions between portfolio components within a modern energy portfolio, it starts to look a little bit like a spider web. And so what I want to do today with my talk is to kind of present a framework for unpacking this and kind of understanding some of these very, very complex interactions that can drive extreme risk, in particular for energy retailers. So what is net position at risk? What is this methodology? Well, it answers a key question, and that is how much uncertainty or risk is there in my net position with some prescribed degree of confidence? And the net position may be of net cash flow. It may be net megawatt hours or net energy position. It may be net CO2 position or GHG position or resource adequacy, et cetera. So really, this net position can span any type of portfolio level attribute, and we need to manage all of these things. NPAR, or net position at risk, really expands the traditional concepts of cash flow at risk or gross margin at risk to apply to any uncertain portfolio level attribute. And uncertainty is the key. If we know how to plan around something, if it's not uncertain, we don't necessarily need to manage the risk. But we're exposed to a variety of different risk factors that are outside of our control, and that's really what net position at risk is intended to manage. It accommodates all the assets and positions in the portfolio, both physical and financial, so it bridges that gap between the two. And it's an ideal tool for energy retailers to understand market exposure, so price risk, but also volumetric exposure that comes along with weather and load variation. And so it brings all of this together and helps us to assess the financial risks that are associated with all these components. So what are some of the components of an NPAR framework? It begins with a simulation of risk factors. And risk factors are going to be particular to each individual portfolio, but generally they include things like weather and load and market prices and renewable energy. These are all the uncertain quantities within the portfolio, and they're all varying on a hyperlocational basis and in a very granular time. So on the image on the right here at the top is an example of a customer demand profile for a residential customer in California, a residential customer class. This is an aggregated demand. And so you can see various trends here. Of course, there's a seasonality that spans across months. This is one look at one particular month in California. You can see that dip in that net demand in the middle of the day. That's driven by rooftop solar. So this is a net demand that's already net of any rooftop solar. But you can see that not only does the demand drop, the uncertainty in that demand rises. So right in the middle of the day, because of all that intermittent generation, there's an increased uncertainty, and that has increased consequences for cash flow uncertainty. In the image on the bottom right, we see a corresponding price distribution, again, for a solar location in California. Now, this is a wholesale price location, but again, you can see that same duck curve phenomenon where the prices in the middle of the day are the lowest of any point within the day, but also it's the maximum level of uncertainty. And so we're not just looking at the level of load or prices, we have to be concerned with that uncertainty around that level as well. So once we have some of these risk factor simulations, we can then go on to value assets within the portfolio. And again, assets can be anything. They can be retail loads, they can be structured transactions, renewable contracts or facilities, storage, thermal generation. All of these things can be valued relative to these risk factor simulations. And then we can finally kind of roll all this together and understand the effectiveness of various different hedging strategies and do statistical reporting to make sense of it all. So that's kind of the general framework that we're talking about here when we refer to net position at risk and really holistic total portfolio analytics. So here are some examples. Here's an example of a weather-load relationship in California. This is for a residential load relative to temperature. That's the scatter plot you see on the left there. And so you can kind of see as the temperature varies on the x-axis, you can see how the load responds. And it's not always extremely intuitive. You can't, as temperatures kind of get up into the high 80s in degrees Fahrenheit, there's not necessarily an extreme increase in load here. It's pretty flat, but you do see that as temperatures fall in this particular residential retail load, there's quite a bit more uncertainty in what that load will be on the low end. And so that's something that will drive uncertainty within this portfolio. When we look at the image on the right, what we're seeing are those confidence intervals in the hourly loads. This shows us not only our hourly shape and the way that shape evolves throughout the year, there's a separate image for each month of the year here, but we also see those risk bands around that. And that is kind of 9 times out of 10, we would expect our demand to be somewhere within those risk bands. And so understanding the nature of that risk helps us to manage the portfolio better in this case. We then move on to the price simulation component. Now here we're simulating wholesale market prices in the sense that that is going to be affecting our costs as an energy retail provider. And so what are some of the things we need to capture? We need to capture the magnitude and the shape of these prices. Often there's a very, very strong relationship between the shape of our load and the shape of the prices, and we can understand that. We also need to understand the uncertainty around that and the profile of that uncertainty and how that changes over time and even hour by hour throughout the year. We have to be able to capture things like negative pricing and basis between 2 different locations on the grid and covariance between price and generation. And then, of course, we have the weather load price relationship. So all of these different risk factors, if you will, they're all hyper-locational. They all vary both by location, but they're also constantly varying in time in response to other things that are going on our grid. So in the images in the bottom left there, these are some examples of a basis relationship at two different points on the grid relative to NP15 pricing. And you can see that the distribution of possible outcomes is completely different based on where you are on the grid. On the right, we're looking at price plots. The one on the bottom right you've already seen, but the one on the top right is a different solar node in California, and it behaves completely differently. So, depending on the location on the grid, that particular location has a signature that is going to impart risk to the portfolio. And so all of this analysis really needs to be done on a location-specific basis. So that's the simulation component of this process, right? We generate a number of possible future outcomes, and we use those then to value the retail book. So once we get into the valuation component, our goal is to value all components against the simulated load and market prices. This is taking into account the specific structures for each retail rate group. Things like time of use schedules, demand charges, indexed rates that might be indexed in some way off of wholesale prices, fixed and variable charges, et cetera. And so the way we usually approach this is to take the overall demand for the portfolio and segment it according to important rate components and or different hourly and seasonal shapes in the load. So a useful split is sometimes to carve out net energy metered customers and non-net energy metered customers because they have very, very different load shapes. Residential, commercial, industrial, agriculture splits along sector lines are also a useful division. And so this process really provides us with a probabilistic view of the retail revenue. We don't just have a single forecast, we actually build some measure of how uncertain that forecast can be, and that helps us to manage risk going out into the future. So finally, what we can do after we have all of this, we've done the risk factor simulations, we've analyzed the revenue coming from our customers as a function of both those risk factors and their retail rates, is we can condense all this into some useful statistical reports, and we can assess the effectiveness of hedging strategies that we have enacted or want to enact. So we generate enormous volumes of data with this process. It's a very data-driven process. But then we can generate statistical reports to start condensing this data into useful reports. So some of the things that you can see here is we can look at hedged and unhedged expected megawatt hour position. We can look at progress toward annual renewable energy certificate targets or cash flow targets. And so on the left here, we see our monthly megawatt hour position for the portfolio. We can see this example getting shorter over time. So we have some hedges that are there in the near term, but we see an increasing exposure to the market over time. And we see uncertainty around that, right? Same thing in our REC position in the image on the bottom right there. And we can see the seasonality and the way these things materialize. And so finally, at the very total portfolio level, what we can develop is a way of assessing hedging strategies and the ability of those strategies to offlay risk from the portfolio, and to do that in a very measured and analytical way. And that's an example here where we're looking at overall portfolio cash flow risk and the impact of various different hedging strategies on being able to reduce that risk relative to these risk factors. So thank you very much for your attention. Appreciate everyone's attendance here. And we have a booth out in the lobby there, so please come and visit us at sequant.io.